Question 1 is about parasailing, which in the exercise is written like this. Just to be absolutely clear right from the beginning, that most of the time in what we do at A level, you would draw it like that. This and this are exactly the same thing. Remember that historically this was the original idea, then people realised that it didn't behave like it had localised alkene groups, and so they came to the conclusion that this was a better description showing the delocalised ring. But both of these are considered to be valid ways of drawing it. It's just that with this one you have to constantly remind yourself, yeah, but they aren't really separate bonds like that. When you come to doing reaction mechanisms as well, it's simpler to use this kind of representation, although actually organic chemists, the reason that they still keep this alive is that it can give you more insight into what happens during the mechanism of electrophilic substitution. Anyway, so just to be clear, this and this, same thing. So the question wanted to know, first of all, what the systematic name of that compound is. So it's based on benzene, and you can see that it has a methyl group there and a methyl group there. So if we call this carbon 1, that's going to be carbon 4. So it's 1, 4, and then remember you've got to put dimethyl to show that there are 2 of them. So 1,4-dimethylbenzene is the name. And the molecular formula, you've got 8 carbons, and then you can count the hydrogens actually pretty easily in this. So you've got 3 there, 4, 5, 6, 7, 8, 9, 10. H10. So remember that when you have something else on a corner, like a methyl group in this case, there is no hydrogen there. And that's very obvious when you draw it out with the Kekulé structure like this, because you can see that carbon has already 4 bonds, so there's no room for a hydrogen. There's just room for 1 there and 1 there and 1 there and 1 there. It's less obvious when you draw it like this, because because the status of this circle in the middle isn't so clear. You can't look at that one and immediately see, oh, that can't have a hydrogen on it. But you have to remind yourself that that delocalized system requires each carbon to contribute 1 electron to the delocalized system, and therefore that's 1 fewer bond that it can actually make externally. So C8H10 is the answer. Part B then wants 2 pieces of evidence to support the idea that it's like that it has a delocalized system rather than localized pi bonds. This is a very common question, and the important thing is that on the one hand you don't want to write a book about each topic, so you've got to be able to say it fairly succinctly, but on the other hand you don't want to not really explain why it supports the idea of delocalization, so you may have to say more than you really want to. So you've got a choice. Probably the simplest one is that all the carbon-carbon bond lengths in the ring are equal. That is important, the wording there. People often lose the mark because they say all the bond lengths in the compound are equal, but of course they're not, because the carbon to hydrogen bond lengths will be different and that carbon to carbon bond length will be different. So be careful with your wording. So all the carbon-carbon bond lengths in the ring are equal. And then you can't say, right, that's answered the question, because they'll say, yes, so what's that got to do with it? So you have to explain the significance of that. So you say localized C-double-C bonds would be shorter than C-single-C bonds within the ring. Okay, so that's made the point that equality of bond lengths is not consistent with that. But then just to spell it out more, but delocalization gives equal pi electron density around the ring, so equal bond lengths. Okay, so that's an example of making sure you've said enough to make the point, but not writing masses, and that's what you aim to do with these kind of questions. This one is stuff you would learn in advance. You know, you have to go into the organic chemistry exam knowing that they're likely to ask you about the evidence for aromaticity, and so you learn these bits of evidence, and then those questions are a gift because you've practiced saying it. Okay, second piece of evidence is the lower reactivity with electrophiles. I think it's best to be precise with that and give the example of bromine. So these compounds, because it asks about compounds like this, so these compounds don't decolorize bromine in the dark. Decolorize, not discolor or decolor. The word is decolorize, means remove, or if you can't remember it, say change it from orange to colorless in the dark. Unlike alkenes, which do that. So that obviously implies that there are no localized CC bonds. But again, I think you want to make the explicit link to delocalization, because that tells you it doesn't have localized CC double bonds, but it doesn't directly make any connection to delocalization. But you can explain that delocalization decreases the pi electron density. Electron density is a very important idea. It means how many electrons are there per unit volume, or or per unit of space around the ring. And so delocalization, because it spreads them out rather than allowing them to occupy specific sides of the ring, decreases the pi electron density around the ring. And if the electrons are less focused like that, they're going to be less attractive. Okay, so making it less attractive to electrophiles. Because electrophiles, remember, are electron pair acceptors, and the more electron density there is focused in a given volume, the stronger the attraction to those things that want to attract an electron pair. So the delocalization decreases the electron density, and therefore explains why it fails to react with electrophiles like bromine. Okay, so that's the second bit of evidence. The third bit of evidence you could have used relates to delta H of the addition of hydrogen to the compound. You're not going to want to do the whole diagram, but let's just quickly remind you of the story and then we'll put it into more succinct words. So remember, if you have an enthalpy profile diagram and we look at the reaction in which cyclohexene, so a non-aromatic compound, reacts with hydrogen, which it will do in the presence of a nickel catalyst, and you find it's an exothermic reaction. Okay, so you add hydrogen and you get cyclohexane. And you get a number something like -100. It's not exactly that, but it's in that region, in the region of -100 kilojoules per mole. So on the basis of that, if the Kekulé structure was right, you would say, well, if we had 3 double bonds, the enthalpy change would be 3 times as big in magnitude. In other words, it would be 3 times -100 and -300. But it would still end up with the same compound, so this level would still be the same, and therefore, running out of space here, but I'll just cheat and put it there. Okay, if it genuinely had localized pi bonds like that, you would say that that would be predicted for localized pi bonds. Okay, because you're just saying, well, we're doing the same reaction, double bond in a ring gets converted to 2 new sigma bonds to hydrogen, and we're doing the same thing 3 times if you believe this structure, so you just expect delta H to be more or less 3 times that, so -300. But when you do the experiment, you find that it's nowhere near, it's not that it's just slightly off, it's nowhere near the correct value. And so this is for real benzene with its delocalized system. So you can still do the reaction, but you find that delta H is about minus 200, is the actual value. So what this experiment tells you is that delta H for the addition of hydrogen to form cyclohexane, is much less exothermic than you'd expect it to be. Okay, so that gap is the effect of delocalization. And what the diagram makes very clear is that what the delocalization does is lowers the energy of the molecule, because delocalization is a favourable thing for electrons to do, and so if it can happen in a molecule, it lowers the energy of that molecule, and therefore makes the addition of hydrogen still favourable, but less favourable than it would otherwise have been. So you could do the diagram, but obviously that may seem like quite a lot of work for you. So if you prefer to put it in words, you can just say that delta H for addition of hydrogen to form cyclohexane. But you've got to be clear what reaction we're talking about. So don't just say delta H is much less exothermic, because I say what delta H? So for addition of hydrogen to form cyclohexane is much less exothermic, or much less negative. Don't say bigger or smaller, because with negative numbers it's very unclear what you mean. That's something we're going to keep saying in lots of contexts through the second year. When you have numbers that have an explicit positive or negative sign, avoid the bigger or smaller thing, because it can be very ambiguous. So just say more negative or more exothermic, but in this case much less exothermic than expected for 3 localized CC bonds. And why is that? Delocalization lowers pi electron energies. You don't have to know why it does that. It's actually a very interesting question, which has to do in effect with the wavelength of the electrons, which is not something that we worry about at A level, but that's the underlying reason. So it lowers the pi electron energies, making the molecule, or making aromatic molecules more stable. Than they would be with localized bonds. So that's possibly the hardest of these 3 lines of evidence to get your head around, but it is important to do that, because of course here you had the choice of not using that one, but you might not have the choice, so make sure you can explain that one as well. C again is a set piece question which you hopefully would have prepared in advance. This picture of how a delocalized pi system is created is something you need to have on tap, ready to bang down on the paper, the same as you would for showing how a localized pi bond would be. So the thing to do is to draw your parasailing molecule as if you were looking at it side on. So you kind of draw the ring a bit flattened like that to give a sort of perspective idea that you're sort of looking at the ring, from the side like this rather than down on top of it. And then the point is that you don't draw on the pi system explicitly, because what you're going to show is how the p orbitals on each individual carbon come together to create that system. So don't draw the circle in the middle, otherwise you're drawing the same thing twice. Okay, so what you do is you say, right, that's my sigma bonded framework, and each carbon has another p orbital with 1 electron in it, and they all line up like that around the ring. And because it's flat, they can overlap continuously all the way around the ring. So you must label it. If you just draw that, they'll say that's just a random squiggle, I've no idea what that's meant to be. That's their rule. If you don't label it, it makes no sense to them. So you have to label it and say, right, these are sideways overlapping p orbitals. Okay, so that's the origin of the delocalization. But then you have to show, well, what does the delocalized system actually look like? Because obviously this is just a shorthand picture. So the second part of the diagram is again from the same perspective, looking at it side on. What you have is that the top lobe of each of these p orbitals, they will all overlap to form a continuous ring. So you can draw it like that, like a halo up above, and then the bottom lobe, you'll get the same thing. So you draw another halo down below, and so you get that. And it's that combination of these two continuous rings of electron density which are the delocalized pi system. Okay, so that's the label diagram that you want. Practice it, have it there in advance, and remember also what it means, that each of these carbons has got 3 sigma bonds already, because if we focus on this carbon, well, actually, just look at this one, you can see it's got a sigma bond to this carbon, a sigma bond to that one, and a sigma bond to the methyl carbon out here. So that's 3 of its 4 outer electrons accounted for. It's the 4th one. There's just 1 electron from each carbon in these p orbitals. And so what that means is that when all 6 of them overlap, you have 6 electrons in the delocalized pi system.